Hi everybody, this is Dylan Byrne with optics.org. I'm reporting out of Quantum West in San Francisco.
I'm here speaking with Anjul Loiacono,
The VP of Quantum Matter Platforms at Infleqtion. She's going to be giving us a product demo, so yeah, please take it away, Angie.
Hi, I'm Anjul Loiacono, and I'm going to introduce to you Oqtant, our quantum matter service. So Oqtant is an ultra-cold research lab that we have made available on the cloud. Essentially what this means is that anybody, anywhere who has internet can create a Bose-Einstein condensate, manipulate it and measure it, and use it for research and education. In 2001, the Nobel Prize in Physics was given for the creation of a Bose-Einstein condensate. So now, in less than 25 years later, anyone can recreate a Nobel Prize winning experiment. So I'm going to show you how you can do this through our web app. So essentially, anyone can sign up on Oqtant and create an account, and you have access to running jobs for free. And so what we will do is we will create a Bose-Einstein condensate. So under the My Jobs, there's a drop down to create a BEC. So it's a BEC generator. And what we have done is the creation of a Bose-Einstein condensate requires multiple cooling steps, where atoms are trapped and effectively cooled using lasers. At that final stage of cooling, those atoms are moved to what's called an atom chip. And that atom chip sends RF signals to a cloud of atoms and gets rid of the warm ones until all you have are atoms that are near absolute zero. So it's the coldest place on Earth. Those RF frequencies are what's really going to create the characteristics of your Bose-Einstein condensate. So what we've done is we've essentially taken care of all of the boring parameters on those first few steps of cooling, and we've given the user the ability to select the final steps to create that Bose-Einstein condensate. And that's what we have on our web app. So there's two settings. There is one for the frequency. The RF frequencies are essentially related to the energy of the atom, or how warm it is. So you can choose how warm of atoms you want to remove from your cloud. The second parameter is the RF power. And the RF power is how hard you want to push those atoms away. So the combination of those two parameters will dictate how cold your condensate is, but also how many atoms are in that condensate. So we're going to create a BEC right now. The first thing you do is you give it a name. So we're going to be very generic and call it a BEC today. This second parameter that we have is called time of flight. You create a BEC, you manipulate it, but then you release it from the trap and you measure its parameters at different times as it falls due to gravity. When it falls, the colder atoms will stay more tightly in place and the thermal atoms will expand faster. So you can choose at what time you want to measure and take an image of that condensate as it's expanding. So we'll just stick with the 12 milliseconds. And then all we do is we hit submit job. So now what's happening, and you get a status indicator here, is that all of the information that we had selected gets sent to our hardware, and now it is running. And so at this time, as we speak, a Bose-Einstein condensate is being created, and now it's complete. So we click on that job, and here is a snapshot image of the Bose-Einstein condensate that we had just created. We provide different information. We include an image of that BEC. We also will provide sort of a smoothed out fit. And then from that fit, we can provide some sliced images that gives you a profile in the X and Y of that condensate. All of this data is available for our users for further analysis. But we also provide a little information in terms of a count of the number of ultra-cold atoms or condensed atoms in the condensate, the temperature. So the temperature of this condensate was 69 nanokelvin above absolute zero. So we're talking about a billionth above absolute zero at that time. So we have just recreated the 2001 Nobel Prize experiment in creating a Bose-Einstein condensate. Once you create a Bose-Einstein condensate, then that's where the fun really happens. And what we have is we have a whole library of demos and walkthroughs through our Python API that allows people to explore actual quantum phenomena. So one example is interference. So quantum interference is really cool because it's a true demonstration of the wave-particle duality. And so what we have here is an example of a multi-slit interference experiment. And this was contributed by a user out of the UK, Dr. Carrie Widener. She created a notebook, ended up demonstrating interference, and then shared that notebook with us. So anybody can share what they discover using our platform.